In our last video, we graphed a reciprocal function. In this video, we're going to be graphing rational or talking about rational functions. Now, a reciprocal function is a special type of rational functions, but now we're going to be talking about the general rational function. A rational function is any function of the form f of x equals p of x over q of x, where p of x and q of x are, and they're both going to be polynomials. And here's the most important part. Q of x will never be 0, and we know we can't divide by 0, and that's the reason why. So here's the steps to graphing these things. Step number 1, we're going to simplify the function. And these steps can be done kind of in different orders, but we'll go over their steps because they're all important, but just know that you don't have to do them in this exact order. We're going to find the x-intercepts, and if you don't remember how to find the x-intercept of a function, if you're looking for an x-intercept, you always set, let's see, I'm going to put it out here, y is equal to 0. And then you're going to find some y-intercepts later, and you'll find those by setting x equal to 0. We're going to find any vertical asymptotes by setting the denominator equal to 0. We're going to find the horizontal asymptotes using these rules. Now, these are very important rules. Remember that we are graphing p over q functions. Okay, if the top degree, if you don't remember how to find degrees, degree is the highest powered exponent. So if it's x squared, your degree is 2. If it's x to the third, your degree is 3. If the degree of the top is bigger than the bottom, if this is like p squared over q to the first, then you will have, let me erase that, you will have no horizontal asymptote. If the degree of the top is smaller than the degree of the bottom, then you will have a horizontal asymptote at y equals 0. If the degrees are the same, your horizontal asymptote will equal y equals, it's still horizontal, the leading coefficient of p over the leading coefficient of q. And again, that leading coefficient is the coefficient on the highest power exponent. And then step 5, we'll identify any holes. And here's how we identify holes. What is a hole? A hole is a point on your graph at which there is a break in the graph. A hole occurs when there is a common factor between the numerator and denominator. And then it gives you the steps on how to find the x-coordinate. We're going to set that common factor equal to 0 to find the y-coordinate, substitute the x-coordinate into the simplified function. But we'll go over all this as we go. Okay, here we go. Step number 1, identify any domain restrictions. This is the way I like to do it. Domain restrictions occur anywhere you would be dividing by 0. What could I plug in for x that I would have division by 0? X will never equal -4. Now, one of two things are happening at those domain restrictions. Either you have a hole or you have a vertical asymptote there. And again, here's the rule. X plus 4 is called a factor. If x plus 4 is a factor of the top and the bottom, you're going to have a hole. That means if there's an x plus 4 on the bottom and top both, there's a hole there. If there's no x plus 4 on top, just on bottom, then you're going to have a vertical asymptote there. So at x equals -4, just like on our last lesson, we have a vertical asymptote. So since there's no common factors on top and bottom here, there are no holes in this graph. Okay, next up, let's go ahead and find our horizontal asymptotes. Now the horizontal asymptotes, we're going to use these 3 rules. You're simply going to look at the degrees. If the degree on top is bigger than bottom, there's not one. If degree on top is smaller than the bottom, y equals 0. If the degrees are the same, we look at the leading coefficients. If you notice here, the degree on the top, the highest exponent is x to the first and same on bottom. So we have scenario 3. The degrees are the same. So your horizontal asymptote is going to be y equals, look at the numbers in front of those 2 leading coefficients that have those highest powers. It's a 1 and a 1. So your horizontal asymptote is going to be y equals 1 over 1 or just y equals 1. That's it. Now let's go ahead and let's draw that horizontal and vertical asymptote. And there those are. Now last step, let's go ahead and let's find our x-intercept. Well, by the way, your range, you can go ahead and say Your range is everything except for where that horizontal asymptote is located. Now your x-intercepts. I told you in order to find an x-intercepts, we're going to set the y value equal to 0. But let's talk about this. A fraction equal to 0. There's only one way a fraction can be 0. If you have something divided by 2, and we know that it's equal to 0, there's only one way that can happen, and that's if the top is 0. Well, could the bottom be equal to 0? No. Remember what we said about vertical asymptotes. You cannot divide by 0 and give you 0. So therefore, to find this x-intercept, all you've got to do really is set the top equal to 0, because that's the only way a fraction can be equal to 0 is if the top is 0. When you solve that, you get an x-intercept at 4. So you can go ahead at 1, 2, 3, 4, and you can plot that x-intercept. And I'm going to go ahead, it doesn't ask me to, but I'm going to go ahead and I'm going to find a y-intercept as well. The way we find y-intercepts is we set our x is equal to 0, and this is even easier. And that gives you a -4 over +4. So that's going to be a y-intercept of -1. And I'm going to go ahead and plot that. And from there, remember, since this is a graph like our last one, it's going to be very similar. It's going to follow the asymptote line, and it's going to follow the asymptote line. And it's going to look something like that. But what about over here? What happens? Well, we need to plug some values in just to see what's going to happen. This is 1, 2. We have an asymptote line at -4. Well, let's plug in -5. And let's get us a point to the left of that asymptote line. So when I find f of -5, on top you have -5 minus 4, which is -9. On bottom, -5 plus 4, which is 1, or -1. When you plug in -5, it gives you 9. So that's going to be located somewhere up here. And that kind of gives you an idea now, okay, my graph is going to follow those asymptote lines. So my graph is going to look something like that. Number 2. Again, step number one, I always find all domain restrictions. X is not equal to 1. Now, we do need to factor this just to see what is a factor of the top and what is a factor of the bottom. So you have an x minus 3 and a 2 on top, and you have an x minus 1 on bottom. So I'm good with that. My domain restriction is x cannot be 1. So what's happening there? Is it a vertical asymptote or is it a hole? Since there's no x minus 1 on top, then I have a vertical asymptote located at x equals 1. And I will have no holes. Okay, from there, let's go ahead and find your horizontal asymptotes. Find your horizontal asymptotes, you look at the degrees. This is just like number 1. If the degrees are the same, you're going to do y equals the leading coefficients. There's a 2 on top and there's a 1 on bottom. So y equals 2 is going to be your horizontal asymptote. And again, that's going to be your only domain restriction. Y will not equal 2 here. So let's go ahead and let's graph those two horizontal and the horizontal and the vertical asymptote. And there those are. Now next up, let's find our x-intercept. To find an x-intercept, you set y equal to 0. But again, since this is a fraction, the only way that y can be 0 is if the top is equal to 0. When you set that equal to 0, you're going to get an x-intercept of 3. So you can come out here to 1, 2, 3 on your x-axis. That's where it's going to cross. And already you know that your graph will look then something like that. Now for a y-intercept, which again I like to go ahead and find, I like to go back to my original. To find a y-intercept, plug in 0 for the x's, so that'll go away, and that'll go away, and that leaves you with -6 over -1, which is 6. So my y-intercept, 1, 2, 3, 4, 5, 6 is going to be right there. So from there, let's follow our two asymptote lines, and we have a look at what our graph's going to look like. Number 3. Now we finally get one that's got a hole. Go ahead and factor the top. It factors into its difference of squares, so factor it into conjugates. On bottom, you have an x minus 1. So therefore, your only domain restriction, x cannot be 1. Now, what happens at 1? If something is a factor of the bottom and also a factor of the top, or it's called removable discontinuity, if I can cancel them out, then I have a hole at that location. So at x equals 1, there's going to be a hole, but I want to go a step further. Where exactly is that hole located in my graph? So what you do, you're going to reduce it. Go ahead and cancel those out. So my original function is pretty much the same thing as x plus 1. To find out the exact location of the hole, take this x value and plug it into your simplified graph, your simplified equation. 1 plus 1 is equal to 2. When I plug in 1, it gives me 2. So I have a hole located at 1, 2. So come here and draw you a hole, an open circle, just like if you were graphing inequalities. That point is not on my graph. So now let's see. I have no horizontal asymptotes, or excuse me, I have no vertical asymptotes because there's no other discontinuity. Since the degree of the top is bigger than the degree of the bottom, I will have no horizontal asymptote either, so none. You can find the x-intercept if you'd like by setting the top equal to set the top equal to 0. So you have x plus 1 times x minus 1 is equal to 0. However, that x minus 1 cannot be 0, so just set x plus 1 equal to 0. So you're going to have an x-intercept at negative 1. Or if you want to put 0 comma negative 1, you can. You're going to have a y-intercept by the way you can find y-intercept is setting both the x values equal to 0. And when you do that, you get a positive 1. But here's the thing. I want you to look at this. This is what my graph simplified into. Y equals x plus 1. That's a line. So my original function cleaned up is simplified into a line that has a hole in it. Okay, so honestly, you can actually just graph this now. Y equals x plus 1, y equals mx plus b, y-intercept of 1, rise 1, run 1 to find the slope, and just plot more points. Here is your graph. However, what's different? Why does your graph not just look like this? What's different about the graph? Why does it look like this? It's going to be a line, but again, it's going to have a hole in that line. What is a hole? Again, your graph comes here, it jumps over, and then it keeps going. Okay, and that's your graph. So your range, you will have one range restriction, and that range restriction is going to be located at the hole. Y will never have a value of 2 because, again, that's where that hole is located on the y-axis. Next up, first step, you always factor. So we have an x plus 5 on top. On bottom, 2 sets of parentheses of an x and an x. You have a plus 5 and a plus 4. Adds to give you 9, multiplies to give you 20. So you have 2 different domain restrictions here. Your domain restrictions are x will never equal negative 4 or negative 5. Now what happens there? First off, notice that you can cancel this to clean it up. So you're going to have a hole located at negative 5. You're going to have a vertical asymptote located at negative 4. So x equals negative 4 is a vertical asymptote. So from here on out, let's do this. Instead of using this to graph this, let's graph 1 over x plus 4. That's much cleaner. We can reduce that. Now, how are we going to use that to graph? We just need to remember that the graphs are identical, except for this one's going to have a hole in it. Now, let's find out the exact location of that hole. The way that you do that, since x is negative 5, take your newly cleaned up graph and plug in that negative 5. And you get 1 over negative 1, which is negative 1. So at negative 5, negative 1, you're going to have a hole in this graph. Let me go ahead and erase that. So let's go ahead and at negative 5, negative 1, 1, 2, 3, 4, 5, negative 1. Let's go ahead and put a hole there. Okay, so from here on out, again, here's what we're going to use to graph because their graphs will be identical now that we have identified where that hole is going to be. Okay, horizontal asymptotes. Next step, you're looking at, for horizontal asymptotes, you're looking at the degrees. And here's the rule. The degree on top is 0, the degrees on bottom is 1 because there's no x's on top. If the degree on bottom is greater, you're going to have a horizontal asymptote at y equals 0. So vertical asymptote negative 4, horizontal y equals 0. Let's go ahead and plot those. Okay, there's those asymptote lines. Now let's go ahead and find an x-intercept. And oddly enough, when you set this equal to 0 and try to solve it, you can't solve that. How can you do 1 divided by something, or how can you set the top equal to 0? You can't. This will not have an x-intercept. Now, however, it will have a y-intercept. To find the y-intercept, you can simply set the x equal to 0. So that'll be 1 over 4. So 1/4 will be your y-intercept. So it's going to cross somewhere right in there. Now, here's your graph. Your graph will now follow those asymptote lines. So since I know that I've got a hole in my graph there that's going to follow on each side from there, and up here, it's going to look something like this. So there's my graph. I do have some range restrictions. My y values will never equal. Okay, look at where you have a horizontal asymptote line. Y will never be 0. And also, y will never equal whatever this whole value is, and that was a -1. So there's your range restrictions. Okay, number 5. Again, first thing we're going to factor this to see what our domain restrictions are. The top is going to have to be factored with bottoms up, so let's come down here, or slip and slide. X squared minus x minus 2. Factor like normal, 2 sets of parentheses, x and x, adds, multiplies, be a -2 and a +1. You moved, you slipped the 2, so now let's divide by the 2. So that leaves you with the bottom factoring into an x minus 1 and a 2x plus 1 when you reduce and whenever you slide it back to the front, or excuse me, that's the top. So an x minus 1 and a 2x plus 1. The bottom, 2 sets of parentheses, factors into x and x, adds, multiplies will be a -4 and a +3. Therefore, my domain restrictions, x will never be, set each of the bottom factors equal to 0, x will not be 4. So my domain x is not equal to -3 or +4. Now again, let's see now if they're vertical asymptotes or wholes. If they're factors of both, if there's removable discontinuity where they cancel out, then it's a whole. However, none of these or neither one of these are that case, so therefore you will have a vertical asymptote at x equals -3 and at x equals 4. Next up, and that puts no holes, none. Next up, let's find your horizontal asymptotes, and to do that, you go back to the original. You look at the powers, the highest powers, the degree, which will be x squareds. If they're the same, you will look at the numbers out front, which in this case are 2 and 1. That's your leading coefficients. So y equals 2 over 1 or y equals 2 is going to be your horizontal asymptote. Let's go ahead and plot or graph those asymptotes. And there we see our asymptote lines. Next up, let's find our x-intercepts. Again, to find our x-intercepts, all we have to do is take the top of our function and set it equal to 0, because again, in order for a function to equal 0, because we're plugging in 0 for y, in order for a function to equal 0, though, if it's a rational function, that means the top would have to equal 0. So therefore, set each factor equal to 0 on top, and you get an x-intercept of 1, and you get an x-intercept of -1/2. So let's go ahead and plot those 2 points. And there they are. And according to that, you can kind of tell what your function is going to do down here. It's going to kind of come down, follow the asymptote line, come down over here, follow the asymptote line. Now here's the only problem. It's going to go up a little bit above there. So when we're talking about the range, that's going to be a little tricky. We might have to use Desmos to find out what this highest point right here is going to be in order to find that range. Next up, you can find a y-intercept if you wanted to by setting all the x's equal to 0, and you can see here that all of that will go to 0, and you'd have a y-intercept of 1/12, which you can see is about right in there. Now we want to see what our function is going to be doing on the right side, or left side of this asymptote and the right side of that asymptote line. So in order to do that, let's plug in some points. Let's maybe plug in a -4 and plug in a 1, 2, 3, 4, maybe a -4 and a 5, just to see what that's going to do in those intervals, -4 and 5. And there's what I got when I plugged in those 2 points, and you can see them. I went ahead and plotted them here and here, and that showed me an idea of what my graph's going to do in that interval. It's going to approach those asymptote lines, so I just sketched it from there. Again, however, when we go to find our range, notice my range is from -infinity up to this point. It doesn't go all the way up to that asymptote line there, so I don't really know what's happening there. So what we're going to do, let me go ahead and finish the rest of our range. The rest of the range is going to be from 2 up to +infinity. And again, since you have that asymptote line at 2, it never touches it. It just starts there. So what we're going to do, we're going to look at Desmos, and you can see that the graph here on Desmos looks identical to what we had graphed there. And to find that maximum value, again, we're just going to click right there. And the highest point here, this nearly a vertex, as you would call it, is going to be here at 0.238.092. So the highest y value there is 0.092. So that's what was it 092 or 0.92? 0.092. So just barely above the y-axis there. Okay, number 6. Again, first step is going to factor this. The top, I can factor out an x squared, and I'm left with an x plus 3. On bottom, we're going to do what adds and multiplies. What adds give you 2, multiplies give you a negative 3. It would be a positive 3 and a negative 1. Notice that you have an x plus 3 on top and bottom. So let's start out with our domain restrictions. X cannot be anything that makes the bottom equal to 0. X cannot be negative 3 or 1. And since you have removable discontinuity at negative 3, then you're going to have a hole at x equals negative 3. And the exact location, again, to find that exact location, what you're going to do is you're going to remove that discontinuity. You're going to cancel those out. And you know that these two functions, the original and this one that I just wrote, are the exact same functions. However, this new one wouldn't have the hole in it. So you can actually plug that negative 3 in to figure out where that hole would be. When you plug in negative 3, you would get 9 over negative 4, so that'd be negative 9/4. So your hole is located, negative 9/4 is negative 2 and 1/4. So negative 3, 1, 2, 3, negative 2 and a 4. So somewhere right around in there is where the hole is going to be located. Now your other domain restriction, since it's not a hole, then it's a vertical asymptote. So at x equals 1, you have a vertical asymptote, and we can go ahead and plot that. Next up, let's go ahead and find your horizontal asymptote. Again, you go back and you look at your original x to the third over x squared. Now, if the top degree is bigger than the bottom, you can go back and look at the notes. There will be no horizontal asymptote, so there's not one. So next up, let's go ahead and find our x-intercept. The way we find our x-intercept is we set the function equal to 0. And you can come right here and you can say equals 0. However, the only way a fraction can equal 0 is if the top is 0. So therefore, you're going to have an x-intercept at 0, 0. When you find that, again, x equals 0 is going to be your x-intercept. So let's go ahead and put that. Next up, not really sure what our graph's going to do. So what we're going to have to do now is we're going to have to plug some points in. We'll make us a t-table because we really don't have a good picture yet of what our graph is doing. So I'm going to take a couple of values. We've already plugged in 0, maybe negative 1, negative 2. We've already plugged in negative 3. So maybe negative 1, 2, and 4. And then some to the right of the asymptote line, maybe 2, 3, and 4. And we're just going to plug those in. You don't have to plug it into your original. You can plug it into this simplified version. And here's what you're going to get. Okay, so there's my points, and I actually had to come over here and I had to do a few more points just because I didn't know what was happening as we approached that asymptote line. So I plugged in a half and I got, or negative, I plugged in 1/2 and I got negative 1/2. I had to go back and recalculate that and do it again. So there's my points, and it's an odd looking graph, but here's what's happening. You've got the graph going in this direction. Then as you get close to the asymptote line, it actually bends down and follows it in this direction. And then same thing up here. It's going to follow it in this direction, then bend around, and then go in this direction here. So there's a picture of what your graph looks like. So your range, the y values go from negative infinity up to this point, which is 0. And then it goes from this point, which is at 1, 2, 3, 4, and it goes up to positive infinity from there. Next problem, number 7. Step number 1, we're going to factor. We have an x minus 6 on top that will not factor, and on bottom we can pull out an x, and we're left with an x minus 6. So your domain restrictions are going to be at 0 and 6. So x cannot equal 0 and x cannot equal 6. Again, I found that by setting the bottom equal to 0. Anything that makes the bottom 0 is undefined. Next up, what happens at those domain restrictions? Anywhere we have removable discontinuity, then we're going to have a hole there. So at x equals 6, there is a hole. Once you simplify it and we see a very familiar function left after we simplify it, then we can plug that x value in to find the y value of our hole. So we have a hole located at 616, so 1, 2, 3, 4, 5, 6, 1, 6, which is somewhere right in there. So we can go ahead and put our hole on our graph. The other domain restriction, which is at x equals 0, is going to be a vertical asymptote. We can go back to the original and find our horizontal asymptote. Since the power on the top is smaller than the power on bottom, then we're going to have a horizontal asymptote. You can look back at the rules of at y equals 0. So pretty much our horizontal and vertical asymptotes are our x and y axis. Then we can plug some points in, plug in 1, you get 1, plug in -1, you get -1. However, this is a very familiar function, hyperbola, that we talked about in a previous section. That's going to look something like this. It's just going to follow your x and y axis, and down here it will do the exact same thing. The only difference was this one had a hole in it because of the x minus 6's. So there's going to be a look at your graph. X-intercepts, there will not be one. It will not cross the x-axis. Your range is going to be from -infinity up to 0, and then from 0 to positive infinity. Next problem. First step, let's graph it, or excuse me, let's factor it. Two sets of parentheses, and x times an x gives you an x squared. Adds, multiplies will be a +7 and a -4. On bottom, x times x gives you the x squared. Adds, multiplies would be a +7 and a +5. So you see your domain restrictions at -5 and -7. Let's go ahead and do those first. X cannot equal -5 or -7. You do have a removable discontinuity at -7, so there's going to be a hole there. So we'll just write it like this. We'll do at 7 comma something, there's going to be a hole. And again, in order to find that hole, we simply remove that discontinuity and rewrite our function, x minus 4 over x plus 5. Let's plug that 7 in, and you'll get a 3 on top and a 12 on bottom. So 3 over 12, that reduces to a fourth. So we're going to have a hole in our graph at 7 comma 1 4. So 1, 2, 3, 4, 5, 6, 7, 1 fourth. So somewhere right in there. Anywhere that we didn't have a hole, we're going to have a vertical asymptote. So at x equals -5, we have a vertical asymptote. Let's go ahead and graph it. Next up, let's go ahead and find our horizontal asymptote. Again, we do it by looking at the leading coefficient. The highest power is in the top and the bottom. Since they're the same, that's when you look at the numbers out front. So y equals 1 over 1, or y equals 1 is going to be our horizontal asymptote. And there it is. Our x-intercept, we're going to take our function, set it equal to 0. And we're going to go ahead and solve that. The only way a fraction can equal 0 is if the top is 0. So that's going to be an x-intercept of 4. So at 4 is 0, which would be 1, 2, 3, 1, 2, 3, 4. Right there is going to be your x-intercept. So your graph is going to look something. You can do some extra points if you would like to. It'll look something like that. The only thing, I don't know what it's going to do over here. So we do need to plug in a point just to see where is your graph located. So we're going to plug in something to the left of that -7, so maybe plug in a -8. So when we find f of -8, you can plug it in right here. It'll be much quicker. That'll be a -12 on top and a -3 on bottom. So when I plug in -8, I get 4. So that's going to be at 1, 2, 3, 4 right there. So that tells me that my graph is going to be up here. It's going to follow those asymptote lines, so it'll look something like that. So the range of my graph is going to be from -infinity up to the asymptote line, which is located at 1, or from 1 to positive infinity. Next problem. Again, step number 1, let's go ahead and factor. Two sets of parentheses, x times x is x squared, adds, multiplies is a -5 and a +1. On bottom, all you can do is factor out the 2, and you're left with the x plus 1. So therefore, you have discontinuity. Your domain does at x equals -1. So x cannot equal -1. Since it is removable, you will have a hole at that -1. In order to find the y value, again, all you have to do is remove that discontinuity, and you have x minus 5 over 2. Now, this should look somewhat familiar. What we can do is, with our distributive property, we can go ahead and divide each of these by 2 and rewrite this as 1/2 x minus 5/2. This is going to be a line. Now we do need to plug our -1 in, and we can plug it in here. It'll be pretty easy. That'll be -6/2, which is -3. So it'll be a hole at -1, -1, 2, 3. Let's draw a hole. But the actual graph is going to be linear other than that. So what you can now do, if you want to go back and use your old slope intercept stuff, this thing's going to have a y-intercept at -2.5, which is right there, -5/2. So it's going to have a y-intercept there. It's going to rise one box and run two boxes. Rise one, run two, rise one, run two. Or it can go, you can do it from the hole as well, down one and left two, down one and left two, over and over and over. And the graph will actually look like this with a hole. So this is a line with a hole in it, is all this graph is. So therefore, our x-intercepts and all this stuff, you can do it the linear way, or again, you can take and set the top equal to 0. Solve it, you're going to get x equals 5. So you're going to have an x-intercept at 5, 0. There is no horizontal asymptotes. There is no vertical asymptotes, either one, vertical or horizontal. The range is going to be all values from -infinity. However, because of the hole, you're going to have to disclude it from -infinity up to -3, union -3 to infinity. Or you can just say everything except for y does not equal -3. You can write that either way.